In September 2022, NASA's DART spacecraft successfully slammed into Dimorphos, a small asteroid moon, marking humanity's first attempt at planetary defense. The mission was designed to slightly alter the asteroid's orbit, proving we could deflect potentially dangerous space rocks. But what happened next shocked scientists worldwide. Instead of the predicted minor course change, Dimorphos experienced dramatic transformations that revealed stunning secrets about asteroid composition and behavior. The aftermath created a cosmic spectacle visible from Earth, fundamentally changing our understanding of these ancient space wanderers and our ability to protect our planet. The perfect bullseye. The moment of impact arrived with surgical precision. At 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART struck Dimorphos at 6.14 kilometers per second, releasing energy equivalent to 3 tons of TNT. Mission Director Nancy Chabot watched from Johns Hopkins Applied Physics Laboratory as telemetry confirmed the spacecraft had hit its target dead center. The refrigerator-sized probe had traveled 11 million kilometers over 10 months to reach this 160-meter-wide asteroid moon orbiting around its larger companion Didymos. Ground-based telescopes immediately began tracking the aftermath, with astronomers worldwide coordinating observations. The impact created a spectacular debris plume that extended thousands of kilometers into space, visible as a bright tail reminiscent of a comet. Within hours, measurements confirmed DART had exceeded all expectations. Instead of the predicted 73-second orbital period change, Dimorphos was slowing down by an astounding 11.5 minutes per orbit. This dramatic alteration meant the mission had been roughly 25 times more effective than the minimum success threshold, suggesting asteroid deflection might be far easier than previously thought. The debris cloud mystery. The impact unleashed a cosmic fireworks display that continued for months. LICIACube, a small Italian satellite deployed by DART, captured stunning close-up images of the collision aftermath, showing massive boulders and dust streaming away from Dimorphos at high velocity. Dr. Elisabetta Dotto from INAF Astronomical Observatory of Rome analyzed the footage, revealing that some debris chunks were larger than cars, ejected at speeds exceeding 500 meters per second. The debris cloud evolved dramatically over time, initially forming a double-tail structure that confused astronomers. Ground-based observations from the Lowell Observatory showed the tail stretching over 10,000 kilometers through space, making Dimorphos temporarily appear comet-like. Most surprisingly, the debris pattern suggested Dimorphos wasn't a solid rock, but rather a loosely bound rubble pile held together primarily by gravity. This discovery revolutionized understanding of asteroid composition, indicating that many near-Earth asteroids might be fragile collections of smaller rocks, rather than monolithic stones. The extended debris emission also meant the orbital change would continue for weeks, as material kept streaming away from the asteroid. The Hubble revelations. Hubble Space Telescope observations revealed phenomena that no one had predicted. Dr. John Yang Lee from Planetary Science Institute led the analysis of Hubble's unprecedented views of the impact aftermath. The space telescope detected boulder-sized debris ejected from Dimorphos traveling at various speeds, creating multiple distinct tail structures that evolved over time. Most remarkably, Hubble observed the debris cloud brightening and dimming in 11.9-hour cycles, matching Dimorphos's rotation period and suggesting ongoing material ejection synchronized with the asteroid's spin. The observations revealed that impact debris continued streaming away from Dimorphos for several weeks after the collision, far longer than models predicted. Spectroscopic analysis showed the ejected material contained silicate minerals and metallic compounds consistent with primitive asteroid composition. The debris patterns also indicated that DART had struck during Dimorphos's northern hemisphere winter, when that region faced away from the sun. This timing may have enhanced the impact's effectiveness by hitting material that was colder and potentially more brittle. Hubble's data proved that asteroid impacts create complex, long-lasting debris systems that could pose navigation hazards for future spacecraft missions. The James Webb discovery. The James Webb Space Telescope made an unexpected discovery that really changed everything scientists thought they knew about the impact. Dr. Christina Thomas from Northern Arizona University actually used Webb's infrared capabilities to look right through the debris cloud and observe Dimorphos directly. The observations showed that the asteroid's surface temperature shot up by about 40 degrees Celsius after the impact, which, points to massive internal structural changes. Even more surprising, Webb detected water vapor and organic compounds in the material that was thrown out, stuff that shouldn't really exist on such a small, airless body. The infrared spectra also showed hydrated minerals being exposed to direct sunlight for the first time, which suggests Dimorphos contains significant amounts of water ice locked away inside its structure. Most surprisingly, Webb observed these periodic thermal emissions from the impact crater that pulsed every few hours, possibly hinting at ongoing subsurface processes, or maybe just structural settling. The telescope even picked up traces of carbon-based molecules, which could represent some of the most primitive organic matter in our entire solar system. All these findings suggested that small asteroids like Dimorphos might actually preserve pristine materials from the early days of the solar system's formation, making them incredibly valuable scientific targets for future sample return missions. The seismic surprise. The impact triggered some pretty unexpected seismic activity throughout the Didymos binary system. Dr. Derek Richardson from University of Maryland used computer simulations to model how DART's impact energy moved through both asteroids. The collision sent shockwaves through Dimorphos that actually got transmitted to its larger companion, Didymos, through gravitational coupling, kind of creating a cosmic tuning fork effect. Ground-based radar observations from Arecibo Observatory's successor facilities picked up on subtle changes in Didymos's rotation rate, showing that the bigger asteroid had also been affected by the impact. The seismic energy ended up causing landslides and boulder movement across both asteroid surfaces, reshaping their geological features in real time. Most dramatically, it looks like the impact actually changed Dimorphos's internal structure, making it less spherical and more elongated as gravity redistributed all that loosened material. Light curve analysis showed that the asteroid's brightness variations changed a lot, which means there were permanent alterations to its shape and surface features. This kind of seismic coupling between binary asteroids had never been seen before, and it suggests that deflecting one member of a binary pair could have some pretty unpredictable effects on both objects. This discovery has major implications for future planetary defense strategies, especially when it comes to binary asteroid systems. The unexpected acceleration. Months after the impact, Dimorphos started showing some really bizarre behavior that just didn't fit any predictions. Dr. Andy Rivkin from Johns Hopkins Applied Physics Laboratory noticed that instead of things settling down, the asteroid's orbital period kept changing, and at an accelerating rate too. By February 2023, Dimorphos was actually orbiting Didymos 33 minutes faster than before the impact, which is nearly 3 times the immediate post-impact change. This ongoing acceleration suggested that DART's impact had set off processes that continued for months afterward. Computer models showed that continued mass loss from the asteroid was creating a kind of rocket effect, where the ejected material acted like a weak but persistent thruster. Thermal analysis revealed that solar heating was causing volatiles buried inside Dimorphos to sublimate and escape, carrying dust and small rocks along with them. The Yarkovsky effect, where absorbed and re-radiated sunlight creates these tiny thrust forces, was also playing a role in the orbital changes. Most remarkably, the asteroid seemed to be losing density, becoming more porous as internal voids expanded. This discovery means that asteroid deflection missions might have long-term effects lasting years or even decades, fundamentally changing how we need to plan and execute planetary defense strategies. The hidden water ice. The most shocking discovery came from analyzing the spectral signatures of ejected debris. Dr. Ian Wong from the Space Telescope Science Institute identified clear evidence of water ice within Dimorphos's interior structure. The impact had excavated material from depths of several meters, exposing subsurface ice that had been hidden for billions of years. This finding, honestly, revolutionized understanding of near-Earth asteroid composition, suggesting that many small asteroids retain water from the early solar system's formation. The ice discovery explained why DART's impact was so much more effective than predicted. Water ice sublimates when heated, creating gas pressure that helped blow material away from the asteroid. Spectroscopic measurements showed the water ice was mixed with silicate dust and organic compounds, creating a primitive mixture resembling comet nuclei. Interestingly, the ice appeared to be distributed throughout Dimorphos, rather than concentrated in specific regions, indicating the asteroid formed in the outer solar system where water could freeze before migrating inward. This discovery has profound implications for asteroid mining and space exploration, as water-rich asteroids could provide fuel and life support for future deep space missions. The finding also suggests that impacts on similar asteroids might release water vapor visible from Earth. The crater that wasn't there. Perhaps the most puzzling aspect of DART's impact was what didn't happen. No clear crater formed. Dr. Sabina Radican from the University of Bern led computer simulations, trying to understand why the expected impact crater never appeared. High-resolution images from ground-based telescopes and LISIACube showed that instead of a well-defined crater, DART had created a broad depression surrounded by redistributed material. The lack of a distinct crater suggested that Dimorphos' surface consists of extremely loose material, more like a pile of sand than solid rock. Impact modeling indicated that DART's energy was absorbed by compacting and ejecting surface material rather than excavating a traditional crater. The missing crater meant that most impact energy went into accelerating debris rather than breaking rock, which honestly explains the mission's unexpected effectiveness. Comparative analysis with lunar and asteroid craters showed that Dimorphos represents a new category of ultra-low-density targets that respond differently to impacts. This discovery has major implications for future kinetic impactor missions, suggesting that loose rubble pile asteroids might be easier to deflect than previously thought. The absent crater also means traditional crater counting methods for determining asteroid ages may not apply to such objects. The Global Observation Campaign. The DART impact triggered the largest coordinated asteroid observation campaign in history. Dr. Nicholas Moskovitz from Lowell Observatory coordinated observations from over 100 telescopes worldwide, creating an unprecedented dataset of the impact's effects. Amateur astronomers contributed crucial observations, with backyard telescopes detecting the debris plume and orbital changes from millions of kilometers away. The European Space Agency's ground-based telescopes tracked debris evolution for months, revealing how impact ejecta spreads through interplanetary space. Radio telescopes detected subtle changes in the asteroid's thermal emissions that revealed internal temperature variations. The global campaign discovered that Dimorphos's brightness varied significantly after impact, indicating major surface changes and ongoing material redistribution. Photometric analysis showed the asteroid's color changed as fresh material from its interior was exposed to space. Most remarkably, some observatories detected secondary debris clouds forming weeks after the initial impact, suggesting ongoing structural collapse within the asteroid. This worldwide collaboration demonstrated that planetary defense requires international cooperation, and showed how citizen scientists can contribute to major space missions. The campaign also proved that relatively small telescopes can make crucial discoveries about asteroid behavior. The future of planetary defense. DART's success has revolutionized planetary defense strategy and opened new possibilities for protecting Earth. Dr. Lindley Johnson, NASA's planetary defense officer, announced that the mission exceeded all expectations, proving that kinetic impactors can effectively deflect dangerous asteroids. The 33-minute orbital change means similar missions could alter asteroid trajectories with years or even decades of advance warning. ESA's Hera mission, launching in 2024, will conduct detailed investigations of the impact site and crater, providing crucial data for future deflection missions. The discovery that many asteroids are loosely bound rubble piles suggests deflection might be easier than expected, but also raises questions about structural stability after impacts. NASA is now developing larger kinetic impactors and considering multiple impact strategies for particularly dangerous asteroids. The water ice discovery has sparked interest in dual-purpose missions that could both defend Earth and harvest resources for space exploration. International cooperation on planetary defense has strengthened, with multiple countries contributing telescopes and expertise to asteroid tracking networks. DART proved that humanity has the technology to defend our planet, transforming planetary defense from science fiction into engineering reality. The mission's success ensures that future generations will have the tools to prevent cosmic catastrophe. DART's impact on Dimorphos proved humanity can successfully defend Earth from asteroid threats, but the aftermath revealed surprises that, honestly, revolutionized our understanding of these ancient space rocks. From water ice discoveries to ongoing orbital changes, the mission exceeded every expectation and opened new frontiers in planetary science. The 33-minute orbital shift demonstrated that asteroid deflection is not only possible, but remarkably effective. Which DART discovery amazed you most? Share your thoughts below. If you loved learning about this historic space mission, hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries.